Welcome to Azure Community Live, an online meeting about Azure for community created by the community. I am your host, Esteban Garcia. The idea behind this online meetup is that anyone, anywhere with an internet connection can be part of this Azure community. I live in Orlando, Florida, and there's a lot of meetups that I used to go to that were in person. And there's many meetups throughout the country or throughout the world that I wish I would have been able to go to. So this is our way to be able to bring all these meetups together, have people to be able, give people the ability to go to any meetup anywhere and have access to all this technology, have access to all this content that typically they wouldn't have been able to get access to. If you want to give back, if you want to be part of this, we'd love to share your story. We'd love to share what you want to share with the world in whatever level. So just get in touch with us over Twitter or YouTube, or just follow our Call for Papers link on our website. It's really up to you. So let me get to the speaker for today. Dr. Sarah Kaiser is going to talk to us about quantum computing, which is an exciting growing field. She's going to be showing us Q#, which is the new quantum programming language developed by Microsoft. Sarah's a Microsoft MVP, and I'm really excited to have her join us today. So Sarah, welcome to Azure Community Live. Tell us about yourself and a little bit more about.
Yeah, thank you so much, Esteban. I'm super excited to be here, and I think it's lunch for you, but it's this is a breakfast talk for me. I'm in Seattle area, so let me get my screen shared here, and we'll get going. So yeah, today I want to talk to you about quantum computers and quantum development. As Esteban pointed out, this is kind of a really exciting growing field, and there are some interesting new kind of Azure offerings on the horizon. So that's kind of the context for. Are we going to change? Yeah. That's kind of the context for why I'm talking to you today. So to give you a TLDR, basically there will be an Azure Quantum service and launching soon here that will basically give you a way, just like any other sort of Azure resource that you could like requisition, you'll also be able to requisition different quantum offerings from the Azure platform. And the reason we're kind of going to talk about Q# today is because that Q# and the Quantum Development Kit, which Microsoft provides and is open source, is kind of the entry point and how you will actually interact with this as a service. So just to give you an idea of where we're going. So a little bit about me. As Esteban mentioned, I'm a newly minted MVP as of this year, specifically for the Microsoft, the Quantum Development Kit in Q#. But I also do a lot of other community development stuff myself. So I run the Q#.community group. I run a meetup group here in Seattle called WICA, Women in Quantum Computing and Applications. And I do a lot of writing. So you can see here some, we're just finishing Learn Quantum Computing with Python and Q#, and I also do a lot of baby books about engineering. So, and I do giveaways on my Twitter quite frequently. So you can find them anywhere you buy books. But before now, I actually did my PhD in quantum computing. And so you can see I used to do a lot of stuff with fiber optics and lasers, and I really like melting things with lasers. So you should try it out sometime. So my first question for everybody, and I realize there's probably a bit of delay, but what have you heard about quantum computing? This is always an interesting question to me because given I've done research in the field, like it's always interesting to figure out like what actual information do people know about it, from pop sci articles, from other books. It's an interesting question. So if you feel like it, drop something in the chat. We'll kind of keep an eye on that. And at least kind of generally when I ask this question, There's a lot of information out there, and some of it isn't super good. So my phone likes to suggest to me articles about quantum computing because it thinks I'm interested in quantum computing, which, okay, granted, that's true. But things like quantum physics can help explain much of the world's suffering. So these are headlines that my phone has showed me at some point here. There are 2 kinds of water in every glass thanks to quantum physics. So, like, I can understand why this topic can be pretty intimidating and sometimes really hard to understand because the information that's out there is not necessarily super clear. So, probably the first thing I want to talk about here is what in the heck is a quantum computer actually then? You can see a photo here of actually hardware for a quantum computer on the right. This entire device would actually sit, well, we'll take a look in a sec. But the main difference we're looking at here is your regular computer is a device that you can manipulate bits in, zeros and ones on your actual hardware. And you write a program to manipulate those bits. A quantum computer really is pretty much the same thing. All you're doing is swapping out the physical architecture for how you're storing that information. So, and we'll take a look. We'll take a look here in a sec of what that difference is. But you still actually write programs, and in fact, you can call them quantum programs. But when you write them like a Q# program, as we'll see here in a sec, they look just, you can write them in Visual Studio Code, you get IntelliSense, you can get, autocomplete. It really does feel like a very similar experience. So, with this new hardware, we kind of have to have a new model for the information that we're storing with that. So we've got our regular binary string. We would, simulate or think about a classical computer, and classical here just meaning any computer that we've ever seen before. Not like as an antiquated Apple IIs or something like that. So a quantum computer, the way you'd represent the information stored in a quantum computer would actually be a vector of complex numbers. So this is kind of where, some of the math can start to get more complicated, and certainly, going from binary to complex numbers and vectors of them can be sometimes kind of confusing and overwhelming, but that's why I'm really excited about Q# and other kind of quantum programming languages, is because that can effectively handle all the math for you. You don't have to necessarily work this all out by hand like I did in grad school, and we have these new programming languages, which is really exciting. So what's a good model for how a quantum computer would actually work in some sense? So you have here on your left your dev machine, so your laptop, your desktop, however you like to work, and you'd be writing your quantum program there. You would send, that would probably be connected to the internet, and you would then send that program to a classical control computer somewhere. Spoiler alert, Azure Quantum, this will be in Azure. And this classical control computer then will take care of sending the, kind of assembly level to down to like literally electrical pulses to control the quantum hardware, which will be sitting in a fridge. And this is not exactly like a fridge in your house. This is a fridge that's sitting at near absolute zero. The main short reason for why that has to be true is because you need to keep these quantum systems isolated from their environment. So, a good way to isolate something is to cool it down real good and just kind of keep any other heat or anything else from interacting with it. And kind of as a mental, so this is, this would be the workflow. But in terms of where we'll actually use quantum computers in your somewhat daily dev routine, if it makes sense, is quantum computers are really like hardware accelerators. It's not going to, you're not going to replace your laptop with a quantum laptop. They really are analogous to GPUs. So, we don't use GPUs to do everything, but we know a certain kind of problem type where it's like, this makes sense to maybe throw on a GPU because it's highly parallelizable. So in a similar way, there'll be, kind of a category of problems where we know, that will actually make sense to run on a quantum computer. And so that's where, and just like GPUs, there are, there's languages like CUDA that are for specific GPU architectures and things like that. This is why kind of it makes sense to have a new language for quantum computers, is because you want to make sure that language accurately reflects what you can do with the hardware. So in general, where might you, I said in your daily dev life for using a quantum computer, where might you want to actually do that? We have a lot of really good ideas for this, and kind of the initial answers I could give you for that are like cryptography, machine learning, and chemistry and material science. Turns out actually to simulate quantum systems, it's actually really helpful to use a quantum system. So particularly for doing things like chemistry simulations and stuff like that, it's actually, those are fairly tractable even for small numbers of qubits. And all of these applications, some of them are, like the chemistry and stuff are more short term. Cryptography is kind of more longer term, just in terms of how many qubits we actually have available. But this is one of the reasons that I'm excited about kind of participating in and growing the quantum community, is because I think there are probably a lot of other good applications out there that we just don't know about yet, because physicists are a fairly isolated group and don't really know what, a daily dev who does machine learning, like what their problems they run into, what are the limiting factors for their workflow. So, having more people understand kind of what's going on here, I think will really help us expand this list. So to that point, we can understand what we can do with different kind of levels of quantum hardware by actually building concrete applications. This is a photo from my lab while I was working and also watching Deep Space Nine at the same time. Because sometimes data taking runs take a long time. But things we need to understand are like, how many qubits will we actually need to do the thing we want? What are the right algorithms to use? And importantly, who's actually going to write those algorithms? Which leads to an obvious question of who can actually write programs for quantum computers. A lot of times people are like, when I talk to them about this, they say like, oh, well, that's not me. You need a physicist or somebody who like fully understands what quantum hardware is and can do. And I would challenge that a little bit and say that anyone listed here can do it. You can do it. And literally everyone can, in the same way that everyone could say learn Python or any other kind of programming language. I want people to feel empowered and not like there's some barrier to entry where you have to understand quantum. Like I've done a PhD in it and I'm still have to repeatedly go back to Wikipedia for stuff. So this is something that I think everybody can get into. So how can we actually learn how to do this together? So enter Q# and the Microsoft Quantum Development Kit. Q#, so to say very concretely, Q# is a domain-specific programming language for expressing quantum algorithms. So kind of like we looked at the GPU model before, it is very specifically kind of designed towards what you can do with quantum hardware, and not, and along those same lines, doesn't allow you to do things that you maybe couldn't. This is kind of a trade-off. A lot of other quantum kind of programming languages or packages or interface things are built, actually most of them are built in Python. But kind of the trade-off with using Python is it can be easier to get going, but there are things you can do in Python that you definitely can't do on a quantum computer. Like, for example, on quantum hardware, you can't just, if I give you an arbitrary register of qubits, you cannot make a copy of that. So, there are a lot of interesting kind of just different things, whether you can physically do or just different algorithms in general that you want to make sure that your language is good at expressing. And as I mentioned before, all of the quantum development kit is actually open source. So that's where I spend most of my time as an MVP, is hanging out on the GitHub repos for all of this and working on issues and adding new features, testing stuff. So if you do a lot of open source stuff, I'd strongly encourage you to go take a look. It's github/Microsoft/quantum. So as to how they actually implemented this, Q# is built on .NET Core. So it's fully cross-platform and portable. You can use it wherever you like, whether you're running on Mac, VS Code, Visual Studio, Linux, whatever you like, you can use it there, which is something I really appreciated because I did a lot of my research stuff on Linux machines, but usually had a Windows machine for for doing university admin paperwork and stuff like that. You kind of need Word and Excel to do that. So you can run Q# wherever you like. To give you kind of an idea of what the architecture for like a Q#, not really called solutions, but what a Q# program would look like. So you'd write your program. You would write some operations and functions, and you could call into similarly a bunch of pre-made libraries. Those are also open source and provided as a part of the quantum development kit. And then that program would basically be hosted or run by usually either a C# or a Python program. But actually now, as of literally the update that went out on Friday, there is a standalone executable as well. So you actually don't even necessarily need a host program anymore. That was a cool new development as of this month's release. But basically, you need something to kind of like host and do the handoff between your Q# program and whatever target machine you're going to run it on. So mostly right now, I've been using the simulator target machine. So you on your just pretty much regular computer can simulate about 30-ish qubits, which honestly is mostly more than any hardware device we have right now. So it's definitely a good way to kind of get started and poke around with some stuff. One of the other interesting target machines you also have access to is a resource estimator. And what that allows you to do, kind of to the point earlier, is say you write a Q# program, you think it solves a problem that you have, and you kind of want to know, like, is this something I could run like next year or maybe like in 10 years? So the resource estimator could actually effectively add up all of the gates and qubits and things that you would need to kind of give you a picture of what resources it would take to run the solution, which I find really helpful. So one other thing, as I kind of mentioned with the host program, is you can actually use Q# from Python. So this was one of the things that sold me on it, because I am a Python developer, and I really enjoy kind of using Python for visualization and data processing, cleanup, all those sorts of things. But you can actually just directly use Q# from Python. So 3.6 and above, but you should probably be on 3.6 at least by now. So yeah. And the one other really neat way to interact with Q# is Jupyter Notebooks. So being a Python developer, I also do a lot of my development in Jupyter Notebooks. And there is effectively Q# kernel for Jupyter Notebooks. So you can run Q# code just as you would like Python code, but in a Jupyter Notebook. And I find this I was literally doing this just last night, working through the solutions to the exercises in the book I'm working on. But like, it's really nice to be able to kind of see documentation in line with your code, and kind of the workflow that Jupyter facilitates. So to the Azure part of this, what is Azure Quantum? To be really honest, I know only slightly more than you do, which is this was announced at Ignite last year. And they did a couple demos at Ignite for showing running on hardware through Azure. So you can check out all the details that are publicly available at azure.com/quantum. And so kind of like as an overview, what services and sorts of things will be associated with this. The obvious one is quantum hardware. So, just like you can access, GPU farms and other sorts of compute resources from Azure, you'll be able to allocate quantum compute resources from Azure. But there will be a lot of other things surrounding it, including a lot of the work that the Microsoft Quantum Group is doing is also kind of around what's called quantum-inspired algorithms and solutions, where basically a lot of the researchers and folks that are working on building the quantum, either algorithms or hardware, kind of end up developing something that is very, like, algorithms that can be speed up classical things that actually can just be run on classical classical hardware. So like better statistical sampling algorithms or better, a lot of it's usually involves with better statistics. So, but you can, that will also kind of be a part of this. So you can kind of bring the problem or problems that you think you're having and that you think quantum solutions might be useful for, and there'll be a team that can kind of help guide you through this process. So to take a look at like kind of what the stack or different services and components here that would be involved. At the lowest level, you have the actual quantum devices, both from Microsoft and from partners. Microsoft has partnered with a bunch of different startups and in November. So you can take a look at bit.ly/Azure Quantum-Ignite if you want to see the talk was recorded and the slides are available. So, but really that's mostly what I know about the Azure Quantum stuff. So currently you can sign up for a private preview, and they say that the private preview will be coming in the coming months. So, but kind of, as I mentioned here, we can get started right now because we can actually use the Quantum Development Kit and we can use Q# and kind of get ready for when we actually can send these jobs to Azure Quantum. So let's actually just do it. I've got a demo going here. Thank you, Docker Desktop, for updating right now. Alrighty. Oh man, I just changed my keycap, so I don't know which one is F11. Nope, there we go. All right, so what I've got here actually is it's a Jupyter notebook, but in disguise. There's a cool plugin called Rise where you can actually turn it into a slideshow. So what I'll be doing here is I'm running actually a Jupyter notebook. So this is I'm running just a generic Jupyter notebook with Python backend, and I'll be using Python effectively as the host program. So I start kind of like you would with any other sort of Python sort of thing. You got to import what you want to do. So I'm going to import Q# here and just check what component versions, and basically check the versions of what I've got installed here. And sometimes that takes it a second. All right, cool. So you can see here now that, so it is kind of interesting. The Python is actually kind of acting as your intermediary to the .NET SDK. So there's a lot of versions here with respect to like the .NET runtime and stuff like that, because it's actually interacting with that as a part of it. So since we are going to actually be interacting with qubits, let's, as a quick reminder, a single qubit can be kind of mathematically represented by a vector of two complex numbers. So this is the funny notation that physicists use. Also, I'm going to make this maybe a little bit bigger. This kind of like, this is called a ket, so with the angle bracket. If you look at a lot of quantum stuff, you'll probably see this, but honestly, if you're using stuff in Q#, don't worry about it. Like, it's a vector, just like any other programming language has vectors. So, but yeah, so we can, and what can we actually do with a qubit? So you can do basically three sorts of things with them. Honestly, they're very similar to what you can do with a classical bit. Like, you can prepare a classical bit or write to it. You can read it at some point. That's pretty much it. You can flip it as a part of other operations. Same thing with qubits. So you can prepare or allocate qubits. You can do operations on qubits, and then you can measure qubits. And kind of one of the weird challenges or puzzles kind of that goes along with working with qubits is, while the information that's kind of, or our way of recording the information that's on the qubit is represented by that vector of complex numbers, when we measure it, we only get a classical bit out. So that's kind of like your measurement is kind of like taking a shadow or a projection of the information that's in that qubit. And so you kind of, this is part of the challenge with quantum algorithm development, is trying to figure out how, given, what can you do with this kind of expanded operation space, but still be able to project it back down to an answer that's helpful to you with a classical readout. So let's actually just go ahead and try out some of these things. So I can prepare a qubit here by, I'm actually using, so here's the Q# package, and I'm using a command called compile, where I'm literally just providing a block quotes of Q# code here. And I'm just saying, please compile this and make it available from Python. So this is kind of like the most brute force way to do it. But now I have this object called prepare qubit, and I'm going to run the simulate method on it. So that's provided by the Q# package. And you can see here that it does something. So what is that something? If we look at the Q# code, what it's doing is, well, firstly, it's opening a namespace. So Q# as a language will probably look more familiar to like more analogous to like C# and more .NET sort of things. But there, like I mentioned, there are a lot of things that are different. So, but like many things, we start by opening a namespace here, and what this code does is it's defining an operation that prepares a qubit. And so we can see it doesn't take any inputs, it has a return type unit, and this using statement is actually how we're allocating the qubit itself. So we're saying using, all right, I want to name it a qubit, and this is the type. This is the built-in type qubit. So, you know, for the length of this context here, qubit will be a valid qubit that I can work with, whether it's coming from my simulator or from an actual target hardware. And then I'm using the dump machine operation here to effectively just show me what does my target device know about, what does it know about at this point in time? So since I'm using a simulator, it will actually report back to me what is that vector that represents the information that I'm working on. So that's why you can see here, this looks very analogous. And if we kind of compare it again to what we were looking at before, you can kind of see this is the same cat that we saw earlier. So whenever you ask for a qubit from Q#, or the Quantum Development Kit, you are guaranteed that it starts in this state, which is considered the 0 state. So you can see how there's a 1 for this row, which is just has the label name 0. You can think of it like basis states. So how can we actually use this to do something maybe slightly more interesting? So in the same directory, and I should point out all of this code and everything is available online in a GitHub repo with a binder link, so you don't even have to install anything to run it and try it. So that there's a link to that in the YouTube chat. But so I also have a Q# file here sitting alongside my Jupyter notebook, and I can actually import things from that Q# file just as if you know, it was another Python file. So I've replicated here what's in that other file just so I don't have to tab back and forth. But so I am writing some new code and putting it in this namespace. So Azure Com Live demo. And I'm defining a new operation. Oops, I did not mean to edit this out. I'm defining a new operation called QRNG, or Quantum Random Number Generator. And it's going to return something called a type called result. The result type is effectively either 0 or 1. It's any valid result that can come from measuring a qubit. So you can see here again, we're using that same using statement, and we're allocating a qubit from our target machine. And then we're doing an actual operation on that qubit. So that just looks like passing the qubit as an argument to an operation. Operations on qubits are kind of viewed as a side effect here. So, you know, there isn't, I'm not going to necessarily, the qubit isn't like a type or something that is all the information about it is being recorded in the type system. Like it's a device, and this H operation effectively says, all right, device over there, go do this thing that we both understand what that means. H here stands for an operation called Hadamard. And you'll probably see the Hadamard operation in a lot of different places in quantum computing because it's the operation that allows you to put things in superposition. So what this code is actually doing is taking this qubit, putting it in a superposition. So rather than being in the 0 state, it's actually kind of halfway between 0 and 1, so that when you measure it, 50% of the time you'll get 0, and 50% of the time you'll get 1. And so we have just a simple return statement here and a operation called mResetZ, which decoded means measure the qubit, reset it, and you're going to measure along in a particular configuration. So the reset here is important because one of the promises that you make as a developer writing Q# code is that when you're done with qubits, you have to kind of put them back the way you found them. So you actually have to kind of reset and put them all back in the 0 state. Now the compiler will let you know if you don't do that. So you don't have to keep track of this in your head, but like that's kind of one of the promises given that all of these effects are considered side effects. So we can import, I just ran the cell, so I'm importing the same code as written in that standalone Q# file. And interestingly enough, I can actually get just like I would kind of query something in Python here and ask for the help about it, the Q# Python package actually makes the documentation strings that you've written for your Q# code available as like Python help here. So you can just, I get this little pop-up that tells me generates a random value, either 0 or 1, by measuring a qubit in equal superposition. So I find that helpful. So let's actually do it. And yay, we got an array with a bunch of zeros and ones. I know that does not seem super impressive, but it actually is, like, it is quantum. It is quantum. And the utility of something like a QRNG is if you were running this on hardware, you are basically basing that randomness on a pure physical process, not a pseudo random process in your silicon somewhere. So, QRNGs are actually a really interesting use case for kind of small numbers of qubits. And we can actually turn on a verbose mode to this same operation and see that when we first get this qubit, it is in that 0 state. And after we apply this H operation, you can see that it has the same amplitude here. There's no imaginary component, but there's the same real component for both 0 and 1. And what that decimal expansion is actually is 1/√2. So, but yeah, what you can see is that those are basically even amplitudes. So that means when you go to measure it, they will have equal probability. So that's great. But obviously 1 qubit is not the end-all be-all, so how do we actually use more qubits? So superposition is one of the kind of 2 main interesting things you can do with quantum hardware that you can't with classical. What can you do? So you can do superposition with even a single qubit, but you need at least 2 to create entanglement. So again, I'm going to import some code, import the operation entangle qubits from an external file, and actually have that simulate. So you can see now, actually here, we have 4 different labels. And what you might be able to guess from that is, so every time we add a qubit, there's 2 to the n possible bit strings we could measure out. So because each qubit you can measure is a 0 or a 1, if you were to measure all the qubits, yeah, you have 2 to the n possible kind of labeled measurement outcomes. And they happen to label them with just integers here. But so it would start in the 0 state here, which would actually be both qubits starting in the 0 state. And you can see something interesting here, that after we entangle them and do the operations necessary to do that, 2 of the possible states have no amplitude, so we would never measure them. But the other 2 have kind of that same superposition, equal amplitudes. So if we take a look, and what that means is this, so the state that's labeled here is both qubits being 0. And the state that's labeled by 3 is both qubits being, if you count in binary, that's 1, 1. So that would be both qubits being measured in the 1 state. But the 0, 1 and 1, 0 case, so basically 1 qubit being measured as 1 bit value and the other being the opposite, will never happen. And so if we actually simulate this, so these are the measurement results for measuring the first qubit and the second qubit, these will always match. So that's kind of entanglement. Another word that's kind of used to refer to it is like correlation. So you can basically associate different qubits. And this is an even kind of association, but you can do it between more than 2 qubits. You can do it in kind of uneven ways. There's a lot of really cool things you can do with it. So let me quickly go back to here and we'll wrap up. So what can you actually do? I know I went through some demo stuff here really quick, but honestly, the best thing you could probably do is just give Q# a try for yourself. There are a lot of meetups now that are kind of springing up everywhere. Obviously, in-person meetups are not going to work out super well right now, but there are a lot of online ones that you can join and learn a lot about both quantum computing more generally and Q# specifically. You can learn by teaching. I really like, once I figure out something, I usually write a bunch of notes to myself somewhere, and I've tried to be good now about just like actually, not putting too much extra time in it and just, turning it into a blog post so that, and I find myself just going back because then it's at least recorded somewhere. But, reading the docs are obviously great, but, sometimes having that kind of personal, like, I installed like 6 different things, but this was the thing I missed, so it can be really helpful, especially for an potentially intimidating topic like quantum computing. And yeah, make the community better than you found it. One of the awesome things about, open source is we all get to work on this stuff together. So you can contribute to the docs if they're not super clear. You can fix bugs. And yeah, it's a really fun kind of place to be. Also, that's my dog taking over my laptop. If I ever get up and leave it somewhere, he immediately goes to it and is like, "This is the thing you're interested in, right?"
So, Sarah, if someone wants to get started and they go to GitHub, is there a project that you say, well, that's the one where I send everyone to whenever they want to get started with this?
Yeah. So I've got the slide right here. So here's some resources that could be helpful for that. So there's a community project called qsharp.community, which is a bunch of the community members, as well as the actual Microsoft employees working on the language design. We've got a pretty active Gitter, so you can ask some questions if you'd like. There is so the primary repo for the quantum development kit on GitHub is just github.com/Microsoft/quantum. So that'll take you to the samples repo and has links to like the runtime and the compiler and the IQ Sharp backend and stuff like that. And certainly all of that is documented at docs.microsoft.com/quantum, so that there's tons of resources there, not only, direct documentation about the language itself, but a lot of like, how do you write a quantum program, a lot of tutorials, things like that. And the obligatory self-promotion. I have a book called Learn Quantum Computing with Python and Q#, and I'm always happy to answer questions and stuff on Twitter. I'm there a lot, and I also I actually live stream doing quantum development twice a week. So if you want to actually see what this looks like in real life, someone working on developing the language, developing applications, hang out with me on Twitch Wednesdays and Saturdays at noon Pacific. So, yeah.
That is, no, that's great. I really appreciate it. There was one question that someone had here. How does someone go about getting a job in computer engineering in quantum computing? Like, what does that look like?
What's that on-ramp? Sure. I think, so one of the things that's been most exciting to me about this field is like really in the last 2 years, a lot of industry has, their ears have perked up and have decided that this is something, Microsoft is investing billions of dollars, I'm sure, as well as IBM, Google, Toshiba, like pretty much every big company now either has a research group that's working on this or groups, kind of like a let's stay on top of this tech sort of team, where basically they want to have people who are experts in this who can help them understand whether, they have an application or use case for it. So like legitimately there are job offerings, like postings right now advertising for, quantum developer, and not just at Microsoft. Like these positions do exist. I think there was a survey, I think last year, trying to project what this sort of need as a role will be in the next 5 years, and they basically projected a huge shortage of folks, just because. I mean, there isn't really formal training programs for this, but that's okay, I think, because really, you can learn the quantum stuff. Like if you actually need to learn the quantum mechanics parts, you can learn that as you go. your skills as a developer, working with arrays, like doing linear algebra, like honestly, Kubernetes scares me way more than any of the quantum computing stuff. Everyone here has a bunch of technical skills to offer. And so I think a lot of these listings often will just be, for people who are familiar with high performance computing or who are familiar with, and even if you're not necessarily writing Q# code for an end application, there's a huge need for people like in DevOps or in, all of the support infrastructure for this. There was just the one classical control computer, right, that I drew in between. That is an incredibly huge stack, spanning obviously the cloud. And so there's tons of space for like, firmware development, basically wherever you enjoy being in the software stack, there is probably a place for where you can work on quantum development stuff. So
yeah, that's great. And I would imagine with whatever's coming next on the Azure quantum side, or I'm assuming people have more access to resources that they don't have access to right now. So it's going to be even more ability. So that's great. I really appreciate you taking the time to join us today. Everyone, make sure you follow Sarah. Go watch her Twitch stream on Wednesdays and Saturdays. Also, go to GitHub and Twitter and Instagram, all the places where she's sharing all this knowledge. I really appreciate you, to getting all this information out. This is such an exciting new field, and I think that. It's great to be able to have people like you that's sharing all this and making this accessible to everyone. So I really, really do appreciate you joining us today.
Yeah, well, I appreciate the opportunity, and I always enjoy talking about quantum computing stuff and lasers and melting things with lasers. So
great, lasers. That'll be our next talk will be on lasers. All right, so again, thanks everyone for joining us today, and come back for more Azure Community Live in the future. This talk will be, the recording will be available on our YouTube channel, so come back and watch it again. Thank you.